Till now, we have discussed 3 problems based on RH criteria. Now, in this presentation, we will discuss problem number 4 on RH criteria. So, let's get started. How many roots of the equation s cube plus 7s squared plus 25s plus 39 equal to 0 lie towards the left of the line sigma equal to -1? In this problem, we are given a characteristic equation and we need to find out the number of roots lying in the left of the line sigma equal to -1. So till now, we have been using the RH criteria in order to find out the number of roots in the left half plane, in the right half plane, and in the imaginary axis. That is, we were finding the roots relative to the origin. But in this case, we are asked to find out the roots relative to this line sigma equal to -1. So before moving on to the solution, we will discuss one more application of RH criteria, which is relative stability analysis. Now please do not misinterpret this with the relative stability. We use the RH criteria in order to determine the absolute stability of the system. We cannot compare the stability of one system with the stability of any other system by using the RH criteria. And this is also one of the disadvantages of using RH criteria. But in this case, we are talking about the stability of the same system relative to a line. So firstly, we will discuss this relative stability analysis, and then after that, we will move on to the solution. So the relative stability analysis is one of the applications of RH criteria, as we have discussed. Already we have discussed two applications of RH criteria. The first application was to determine the range of values of k for which the system is stable. The second application was to find out the marginal value of k and the frequency of sustained oscillations. And this is the application number 3. Moreover, it is used to find out the number of roots of the characteristic equation relative to a line sigma equal to -a. Let us consider a pole zero diagram in which the real axis is the sigma axis and the imaginary axis is the j omega axis. Now if we consider a line sigma equal to -a in the sigma axis, then we can find out the roots relative to this line. That is, we can determine the number of roots of any characteristic equation lying in the left of this line, in the right of this line, and on this line. Initially, we were using the RH criteria in order to find out the number of roots in the left half plane, that is in the left of the origin, in the right half plane, that is in the right of the origin, and in the imaginary axis. That is, we were discussing the number of roots relative to origin. But now we are talking about the number of roots relative to this line sigma equal to -a. That is, we have shifted the origin to the line sigma equal to -a. And that is why this concept is also called as shifting of origin. So how we can do it? So in order to find out the number of roots relative to a line sigma equal to -a, we need to replace s in the characteristic equation with s minus a. So if we are asked to find out the number of roots relative to sigma equal to -a, we will replace all the terms of s in the characteristic equation with s minus a. And then we will form the Routh array, and then we will move on with the same procedure of RH criteria. That is, we will form the Routh array, and then we will examine the number of sign changes in the first column of Routh's array. So I hope you understood the concept of shifting of origin or relative stability analysis. Let us now apply this concept in order to solve this problem. So coming back to the problem, we are given a characteristic equation s cube plus 7s squared plus 25s plus 39 equal to 0, and we need to find out the number of roots of this characteristic equation in the left of the line sigma equal to -1. So we will be applying the shifting of origin concept, and from this concept we know that if we want to calculate number of roots of characteristic equation relative to sigma equal to -a, we need to replace s in the characteristic equation with s minus a. In this particular problem, we need to find out the roots relative to sigma equal to -1. So the value of a is equal to 1 here. So we will replace s in the characteristic equation with s minus 1. So moving on to the solution, we are given the characteristic equation f of s equal to s cube plus 7s squared plus 25s plus 39 equal to 0. And if we want to calculate the number of roots relative to sigma equal to -1, we need to replace s in the characteristic equation with s minus 1. So f of s minus 1 will be s minus 1 whole cube plus 7 multiplied with s minus 1 whole squared plus 25 multiplied with s minus 1 plus 39 equal to 0. See, we have replaced all the terms of s in this characteristic equation with s minus 1. Now, if we open this bracket with s minus 1 whole cube, we will have s cube minus 3s squared plus 3s minus 1. We know a minus b whole cube is a cube minus 3a squared b plus 3ab squared minus b cube. So if we open the bracket with a minus b whole cube, we will have these four terms. Now, if we open this bracket with a minus b whole squared, we will have plus 7 multiplied with s squared minus 2s plus 1. Moving on, if we multiply 25 in this term, we will have plus 25s minus 25 plus 39 equal to 0. Now, if we open this bracket by multiplying 7, we will have s cube minus 3s squared plus 3s minus 1 plus 7s squared minus 14s plus 7 plus 25s minus 25 plus 39 equal to 0. We have opened this bracket by multiplying 7 with these three terms. Now we can see that we are having only one term of s cube, two terms of s squared are there, minus 3s squared and 7s squared. So if we solve this, we will have 4s squared. Now if we observe, we are having three different terms of s power 1, 3s, minus 14s and 25s. If we solve this, we will have plus 14s. And if we observe the constant terms, we have minus 1, plus 7, minus 25 and plus 39. So now if we simplify this equation, we will have f of s minus 1 equal to s cube plus 4s squared plus 14s plus 20 equal to 0. And this is the modified characteristic equation we will use in order to find out the number of roots relative to this line sigma equal to minus 1. So I hope you understood this concept till now. We will now use this characteristic equation and we will apply the RH criteria onto this. So let us now move on to form the Routh's array using this characteristic equation. So moving on to form the Routh's array for the characteristic equation f of s minus 1 equal to s cube plus 4s squared plus 14s plus 20 equal to 0. So let us form the Routh table and we will have the highest power of s and the subsequent power of s. Now we can fill these two rows by using the coefficients of this characteristic equation. So we will have 1, 4, 14 and 20. We know the coefficients are 1, 4, 14 and 20. So we can fill them like this: 1, 4, 14 and 20. And rest all the coefficients will be 0. Now moving on to the next row, which is the row of s power 1. So the first term in this row will be 4 multiplied with 14 minus 1 multiplied with 20 over 4. And if we solve this, we will have 9. And the second term of this third row will be equal to 0 because it will be 4 multiplied with 0 minus 1 multiplied with 0 over 4. So it will be equal to 0. Now moving on to the last row, which is the row of s power 0. And this term in the last row will be equal to 20. Because we know that if this term is equal to 0, we can directly copy this term to this row. Moreover, this term will be 9 multiplied with 20 minus 4 multiplied with 0 over 9. And if we solve this, we will have this term as 20. We also know that the last term of the Routh array is the constant term of characteristic polynomial, which is equal to 20. So this is the Routh array for the given characteristic equation. Let us now examine the number of sign changes in the first column. So we can see all the terms in the first column of Routh's array are positive. So the number of sign changes we can say is equal to 0. Now we can say that the number of sign changes in the first column of Routh's array will tell us the number of roots of this characteristic equation in the right of sigma equal to minus 1. But in this case, the number of sign changes is equal to 0. So we can say that the number of roots of f of s minus 1 in the right of the line sigma equal to minus 1 is equal to 0. So what does this mean? Yes, all the roots of f of s minus 1 are in the left of the line sigma equal to minus 1. So if we try to plot all the roots of this characteristic equation, we have this line sigma equal to minus 1. And we know all the roots of this characteristic equation f of s minus 1 are lying in the left of sigma equal to minus 1. So we will have all the roots in the left of sigma equal to minus 1. And we know that the roots of characteristic equation are the poles of the system. So all the poles of the system are lying in the left of sigma equal to minus 1. In this problem, we were asked the number of roots of the characteristic equation lying in the left of sigma equal to -1. So we modified the given characteristic equation by replacing s with s minus 1, and we prepared a new characteristic equation. And then we applied the RH criteria, we formed the Routh array, and we examined the number of sign changes. And we found that all the roots are in the left of line sigma equal to -1. Now if I ask you whether this system is stable or not, of course it is stable because they are lying in the left of line sigma equal to -1. So already they are lying in the left of origin, they are in the left half plane. So the system is absolutely stable. So I hope you got this problem and the concept of relative stability analysis, or we can say the concept of shifting of origin. Now I want you all to go through the steps we discussed in this concept, and then after that I will give you one homework problem. I hope you're done. So this is your homework problem. Try this problem on your own, and if you're able to do it, do let me know in the comment section. In the next lecture, we will solve one more problem based on RH criteria. As of now, we are done with this lecture. Thank you for watching this lecture. I'll end this one here and I'll see you in the next lecture.